Hi. Let's continue. So today I wanted to go to the heart of this topic called Lebesgue differentiation theorem. Uh, I start from the following theorem. Suppose suppose f in L1 of R. Then for almost all points, say B in R, the following holds. Uh, f of B equals, so we take integral from B minus T to B minus plus T f d lambda, take 1 over 2t, so it is the mean value of the function from b minus c to b plus t, and takes limit when t goes to 0. So it holds automatically for a continuous function. And this theorem says that for continuous function f, it is true for any b, and for just measurable function in L1, so its integral of its modulus is finite, it holds for almost all b. Yeah. Or we can write limit 1 over 2t integral from b minus t to b plus t f of x minus f of b d lambda equals 0. So b is constant, x is variable, lambda is Lebesgue measure. So limit when t goes to 0. T goes to 0. No, okay. Now let us start proof. It is, I would say, a little bit technically interesting proof. The proof is based on approximation of function f by some continuous function. We know that it is possible. Uh, there exists let me write. Let delta positive there exists a continuous function, say h k of x, such that norm f minus hk 1 less than delta divided by k times 2 to the power k. No, here can be any number, any small number. No, we choose this, and then we'll see what happens. Then this means that f equals hk plus fx x plus some function psi of x, and hk is continuous, and norm psi in L1 less than delta k times 2 to the power k. No, why so we'll see in a short time. So Xi is really small in L1, and this means that the set where Xi is large is has a small measure, or the set where Xi is small is takes almost all of the real line. So we'll define the set bk, the set of x, such that model ck of x, this function ck, less than 1 over k, less or equal, and model c k star of x less or equal 1 over k. Yeah, so it is the set where this and this are small. Now let's consider the complement of this set bk. R minus bk is the set of x such that either this is more than 1 over k, or this, or both. Model psi k of x more than 1 over k, union with the set over x, x such that k star of x more than 1 over k. Now let us denote it by dk union e k. Yeah. And now we can use these two inequalities, the Markov inequality and Hardy-Littlewood inequality, which we found last time. So dk is the set where this function psi is more than 1 over k. So by the Markov inequality. Uh, 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 Measure of uh, decay is less than so mark of inequality, a measure of the set where it is more than c, the function is more than c, is less than this 1 over c times L2, L1 norm. Here C is 1 over K. 1 over 1 over K times norm of function C, norm of C in L1. But it is less or equal norm C in L1, CK CK in L1 less than 1 over 1 over K times delta divided by K times 2 to the power K, which is equal to 1 over K here and K here cancel, delta divided by 2 to the power K. The measure of outer measure of EK is by Hardy-Littlewood inequality. This measure less or equal 3 divided by 1 over K norm CK 1, which is less or equal than 3 delta over 2 to the power K. Yeah. So to this end, we had a great struggle to prove the Hardy-Littlewood inequality, and this means that it was done to have this estimate of measure of EK. And as a result, measure of R minus BK minus this BK is less or equal than sum of measure DK and EK for delta divided by 2 to the power K, no, which is delta divided by 2 K minus 2. We can write this way. And now let us write, define B equals intersection of all BK, okay, from 1 to infinity. Yeah. B is the set, and R minus B is less or equal than sum R measure R minus BK, okay, from 1 to infinity. Yeah. It is less or equal sum of delta 2 K minus 2, K from 1 to infinity, which is equal to And now consider the point. Consider a point. Okay, I don't need this anymore. We have this final estimate. So that the measure of complement to B where uh, yes, so we have a sequence of the function ck of x. It's not one function, it is a sequence of the function. And we consider the set where both the function ck is small and ck star is small. Yes, and because ck tend to zero, the L1 norm tends to zero, then we can have this set such that the we have to go in this direction. The measure of the complement to this set B is small. Okay, now we can go to the main part of the proof. Suppose the point B in B capital. So in all of this, hence B in BK for any K. Because B is intersection of all dk. Now let us fix some k. And consider this difference which we wanted to prove that it goes to 0. So 1 over 2t integral from b minus t to b plus t. Module fx minus f of b d lambda. Yeah. So it means deviation fx minus fb. Now let us transform it. It is equal to no, let me start from the beginning. Module 1 over 2t integral from b minus t to b plus t fx minus f of b d lambda. It is less or equal 1 over 2t integral b minus t b plus t module of this fx minus fb d lambda. Yeah. So module integral is less than integral of module. We know this inequality. And now we transform this less or equal 1 over 2t Integral of what? Uh, fx minus hk of x. No, it is k of x plus model hk of x minus hk of b plus model hk of b minus f of b. d lambda. Yeah? And now let us estimate all these integrals separately, one by one. The first, 1 over 2t integral b minus t to b plus t of what? Module fx minus fb d lambda. It is equal 1 over 2t integral b minus t to b plus t module ck of x d lambda. No, fx minus hk of x. Yes, now it is ck of x. And by definition of the set, uh, uh, is less or equal uh, supremum over, say, s, 1 over 2s, integral from b minus s to b plus s, module ck of x d lambda. Yeah? So we consider d, instead of one t, we consider all positive s. Yeah? And which is simply c star of b. Yeah? And c star of b, because b in this bk, so there c star k of x is less than 1 over k. So it is less than 1 over k. So the first term is less than 1 over k. So this is I would say, center of the proof, that here appears the maximal function of hard little wood. Yeah, so we cannot directly approach to this integral, but we simply chose the set where this integral is small. Yeah, so it is very good catch. Now the second term, the last term, h uh, the next term, hk of b minus f of b, uh, 1 over 2t integral b minus t, b plus t, what this term, uh, hk of b minus f of b, yeah, d lambda, but it is a constant. This is a constant and this constant. It is the difference between function at the point b and the approximate function hk. We know that it is simply uh, model. Simply model c k of b. And again, and the set bk, ck of b less than 1 over k. Less than 1 over k. And last, we have this integral. They have this integral, hk of x minus hk of b, the last term. So, unfortunately, I have to erase this part. 1 over 2t integral from b minus t to b plus t, hk of x minus hk of b, dx. Why I write dx? Because hk is a continuous function. Yes, hk is a continuous function. And the integral of continuous function is defined in simple way. It is a Riemann integral. Yes, so I don't need any sophistication here. And if h uh, so h is continuous, then I would say less than 1 over 2t times length of this interval 2t times supremum model hk of x minus hk of b over the interval model x minus b less or equal than t. Yeah, it is the simplest estimate of integral. So integral model of integral is less than supremum model of function times the length of the segment of integration. Yeah. No, this is 1. And this goes to 0 because the function hk is continuous. Hk of x continuous. It happens that this goes to 0. as t goes to 0. Yeah. So here, continuity of these approximation planes. Yeah. So this means the following. This means that if B in BK, then for all sufficiently small t positive, the following is true. 1 over 2t integral from b minus t to b plus t module f of x minus f of b d lambda less than, no, these first two terms give less than 1k, less than 1k, and it can be also done less than 1k if t is sufficiently small. So less than 3 divided by k. Yeah? But b in bk for all k. Yeah? No, all integer positive k. This means that this integral becomes, no, this ratio, or this left-hand side, becomes less than 3 over k, eventually, when t is small enough, for any k. Yeah? So this means that 1 over 2t integral b minus t, b plus t, model f x minus fb d lambda goes to 0 as t goes to 0. Yeah. So this is the end of the proof. So in this proof we used creatively all the previous all the previously found devices, and so we have already proved it. And before going to the Newton-Leibniz theorem or fundamental theorem of calculus, let me describe this issue of density of sets, which was burning and itching me for a long time. It is, in fact, one of the finest results of all Lebesgue theory. So it is called density of a measurable set. So we know that the measurable sets can be quite tricky, and I hope to show a good example a little further. And the question is the following: given a set, so given a set, say A in is a Lebesgue measure set, no, of R. Lebesgue measurable set on R. And take point B in R, yeah, and consider the following thing. It is 1 over 2B, measure of the set A, intersection with the segment B 1 over 2T, B minus T, B plus T. Yeah. Consider this piece of the set. So the set is somewhere here, and consider the point B. It is B minus T, B plus T, and the part of the set here, and divide it by the length of this segment. So this is the mean density of the set A on B minus T, B plus T. Yeah, so it is mean density defined by this formula. And consider a limit when T goes to 0 of all this 1 over 2T integral measure A, B minus T, B plus T. Yeah? If this limit exists, then we can, it is natural to call it the density of the set at the point B. Set A at the point B. Yeah. If such thing exists. No, in particular, for example, if A equals, say, say 0, 1 in R, yeah? This is A. Then if B is here or here, then for short, for small t, all this segment is beyond our set A. So the density is 0. Here the density by the same reason is 1. And here at the endpoints the density is 1/2. Yeah. And so again, the question, is it possible that we have a set such that its density is 1/2 at every point of the line, for example? Yes. And it turns out that it is wrong. Such thing does not exist. And the theorem, let me, it is d a at the point B. Yes, it is notation for the density, if such exists, such density exists. Uh, First, dA of B exists for almost all B in R. And second, for almost all B in R, dA of B equals 1 if B in A, 0 if B is not in A. Yeah? No, what it should be? It is like in this example, here we have two outliers, the point 0 and 1, but they have measure 0. Yeah? So how it is proved? No. Proof. Consider fx equals characteristic function of the set A, which is 1 at the point of A and 0 if the point is outside of A. Yeah? This is the function f of x. No, it is a function. No, we consider this function on a finite piece. In fact, it does not matter because anyway we take to find the density of the set at the point, we have only take into account only the points which are close to point B. Yeah. So then, for almost all B in R, we have the following limit 1 over 2t integral from b minus t, b plus t, f d lambda equals lim when t goes to 0 equals f of b. Now, in particular, 1 over 2t integral from b minus t to b plus t characteristic function of x d lambda equals simply measure of a intersection with b minus a, b plus a. Yeah, it is measure of outer measure of this set. Yeah, and no, trivially this means so the left hand side equals this limit 1 over 2t measure a intersection with b minus t, b plus t t goes to 0 is simply dA of b. Yes, but the same definition. Yeah, and so we see that dA of b equals characteristic function a of b for almost all b. Exactly what we thought. So this function, characteristic function, no, gives us the tool, and so the Lebesgue measurable sets, they are not diffuse. Yeah, they cannot be diffused so that the density is everywhere small. No, say 1/2, for example. Now, what else? I promised also to prove the fundamental theorem of calculus. I will do it now. Where it is. Aha, here it is. Theory of calculus. It is the following. We have a function f of x. It is no, Lebesgue measurable functions. I don't say say f1 is finite. Yeah. No, again, because this theorem is so to say local, we are not interested in behavior of f very far. We can consider the functions on say segment 0, 1 or any other finite segment. Yes, no, consider on 0, 1. And suppose f capital X equals integral from 0 to x f of t d lambda equals integral over the set 0x f d lambda. It is f capital, so to say, primitive function. And the theorem f prime of x equals limit f x plus t minus fx divided by t when t goes to 0 exists for almost all x. Let me write, if I wrote b, let me write also b. For almost all b, and f prime of b equals f small of b. prove. No, let us write this ratio. F of b plus t minus f of b divided by t equals simply 1 over t integral from b to b plus t f d lambda. Yeah. And f of b plus t minus f of b divided by t again minus f of b, f small, equals 1 over t integral b plus t f d lambda minus f of b. Now we can put f of b under the integral equals 1 over t integral from b to b plus t f of x minus f of b d lambda. Yeah, because integral f of b from b to b plus t is exactly f of b times t divided by t is this. So we have this inequality, equality, yes, and then we have this powerful theorem which say that it goes to 0 when t goes to 0 for almost all b. No, in this case, b in 0, 1. Yeah. This, no, okay. Let us write. So let us put it in the model. Under the model, less or equal 1 over t integral from b to b plus t module fx minus f of b d lambda, and less or equal, no, instead of integral from b to b plus t, we write integral 1 over t integral from b minus t to b plus t module fx minus fb d lambda. And this goes to 0 when t goes to 0 for almost all b. Yeah, now it is full correct. No, that's it. So we proved this fundamental theorem and can be proud. Now, I wanted to tell a few words about this phenomenon on, say, diffuse sets. Yes, so let me explain this example. So diffuse sets. So what is diffuse sets? Let me say theory. Um, there exists a set, say A, Lebesgue measurable set, such that uh, if you take A intersection with any segment I, for any segment I, is first positive and second less than length of I. Yeah. So there is no full piece. It does not contain any full segment or segment with no minus set of measure 0 on one hand. On the other hand, it has no real gaps. So in any small segment, whatever, we have some positive measure, part of measure A of set A of positive measure. Yeah, it is really interesting. No, again, it's enough to work in the segment 0, 1. Now how to construct this set? I construct the characteristic function of this set, first of all. And then the set is defined a set of points where characteristic function is 1. And Fk is characteristic function of the set Ak, say of x. Now I construct it as a limit. It is I construct the sequence of these characteristic functions, and it turns out that these characteristic functions, this sequence goes to some limit for almost every point, and this limit will be the characteristic function of our set. So no, the first is from f1 of x equals 1. Yeah. Let me draw it. This is characteristic function of the set f1. f2 of x equals 1 1/4, for example, 0 1/4, no, let us take 2/5, for example, 2/5 less than x less than 3/5, and 1 it is when 3/5 less than x less than 1. So it looks like this. It is 2 3/5. So here is 1, here it is 0, and here it is again 1. So this is characteristic function 0, 2/5, 3/5, 1. uh, this characteristic function. This is our set. And now I wanted to describe the inductive stack. So these sets are constructed by induction. Suppose at the kth step, I equals 0, 1, I equals I1, I2, and so on, In. No, n depending on k. Yeah, this. They can be different length. Now they do the following. We take I1 and take in the middle of I1 the segment J1. So this is I1, this segment, yeah, and this is small segment J1. J1 segment M segment in the middle of IM, and length of JM equals length of IM divided by, so it is step k, no, something large, k factorial, for example. Yeah. So here we have also such thing, and here something, and here, and so on. Yes. On JM, the function f k plus 1 is different by km, fm. If fk on jm equals 1, then fk plus 1 on jm equals 0. And 0 goes to 1. So if 1 goes to 0, and 0 goes to 1 on Jm. So on each of the segment I1, I2, and so on, the function fk can be either 1 or 0, and on this small segment Jm, we change it to opposite, from 1 to 0, from 0 to 1. Yes? And the key is that the length of this Jm, the ratio of length of Gm to the length of Im decreases rapidly when k goes to infinity. Yeah. No, I think k factorial is already good. And so what I reach this way? No, first of all, why the first statement statement 1, for almost all x, there exists limit fk of x when k goes to infinity. Yeah? You ask me why it happens. I will tell you why. Because of our now old friend Borel-Cantelli lemma. Why? Consider the set jk equals union of jm. No, if it is done on the case on the step number k, no, we have also to add here k m from 1 to n of k. Yeah. In fact, n of k in this construction is 3 to the power k. So we started from one segment, then appeared one in the middle and two on the flank, and so on. So the length of jk, yeah. So it is we take into the each of ik segment which whose length is 1 over k factorial of all length, and we did it in each of these segments, and so the length of jk is equal length of j of it is equal simply 1 over say 2 factorial times 3 factorial times 4 factorial and so on. So at every times k factorial. So at every step, the total length of this set, which is consisted of many segments, is decreased, multiplied by 1 over k factorial at this step number k. Yes? This means that it decreases very fast, and the sum of length of jk, k from 1 to infinity, converges. In fact, I needed just this. And so we have simply a sequence of sets jk such that their length, the series made of their length, converges. If it does converge, then by the Borel-Cantelli lemma, for almost all x is true, that x is the set of only finite number of sets jk. Yeah. No, this means that if for some k X is in JK. Хоче брися сюди. I'm sorry, it's my dog. On some at some set JK, then the value of the function fk changes from 0 to 1 and from 1 to 0, depending on what it was before. Yeah? But this lemma Borel-Cantelli guarantees that for almost all x, this happens only finite number of times. And after that, it stays constant. Yeah. No, that's it. And the claim is that this set does not contain any segment. Yeah. No, again, it does not contain any segment. First of all, we started from function from the set which was all this segment, and the total measure of the sets where this segment changed at least once is less than 1. So for some positive set here, some positive set of positive measure, it remains in the set A k for all k. Yeah. So this means that at least something remains here. Now, if at the first step we had this picture, yeah, this picture. So it remains only set here, and in the middle, no, let me draw it smaller, like this. In the middle, we have a gap. Then next time appeared some piece of this set here. I draw the characteristic function. And if the sizes of this segment J number K upstairs decrease fast enough, then we have the following thing. Here also in the segment from here to here, after all future changes, some set of positive part will remain here. Yeah. Here we have a set of length, positive length, where it was 0, and by the same reason, after all possible changes future, some part of this in this small segment where initially we had no elements of the set A will be free of elements A, because we changes it on the set of smaller and smaller measure, and totally the measure where we changed this set, which is empty here, does not reach the total set of this small segment, and so on. So this means that any segment will have common part with this set A. So this set A is the set where this limit equals 1. This limit. And this is Borel set because it is intersection of a sequence of sets, each of which is union of finite number of segments. Yeah, it is growing but finite number. So it is clear that this Borel set, but it is it is now diffuse set. Yeah, so it neither so this set has a common part with any segment of positive measure, and its complement has the common part of positive measure with any segment. So this is example, and I wanted to tell that similar situation appears in no okay, so what is the moral of this? Moral is that this set does not have this property that its local density pose at a point is different from 1 or from 0, of course, but it is closer to it in sense that its mean density on arbitrarily small segment is different from 1 and different from 0. Yeah, so no, it is not a very great deal, but such constructions appear in a really modern study and quite applied. So maybe I will have chance to tell you about it. Now let's finish with this. It is now I start having fun of this course, and no, if necessary, I will continue if I will not see you in person. For now, have a good time. Bye.